Now, just a couple of announcements before we get going today. I'll try to keep these brief. Now, Whitney, you're a Lawson student, right? And you're a transient or a Lawson? You're a Lawson student, too. Do y'all know about the math team, math club? Okay, all right. It meets this summer every Tuesday afternoon. Unfortunately, that was yesterday, 4:30 to 5:30 in the Science Building on the Birmingham West Campus, Science Building C100. Mr. Gerasi is the coach for it, and they are doing several things. One is getting ready for the competitions coming up in the fall, but also just forming a club and doing that type of thing. Okay, it should be a lot of fun. I think it is. STEM Jobs is a company that, goodness gracious, scare me. No, I'm just kidding. Okay. Is a company that I don't know why we're publicizing for them, but they've released a new tool to connect classroom to careers in STEM, science, technology, engineering, and math programs. So it's called the STEM Type Navigator. Okay, if you want more information on that, please see it. And not before about the math club, math team. They meet every Tuesday afternoon, 4:30 to 5:30 this summer. They'll be meeting again in the fall. I don't know the time. So, okay, and Tyler is here, but I've got to find you. There you are. Okay. Now, let me say this too. I hope I've said it plenty of times in the past, but let me go again. Now this, of course, one of my best classes ever. And here's DeMarcus talking about best classes ever. Okay. Is actually leading the pack as normal in getting research papers in. 3 so far. 3 out of, 15 students? 3? That's 1/5 of the students have turned in a research paper. Remember, we only got a couple weeks left in the term. Please don't postpone this too long. Get it done well, get them into me. Okay, on that also, test 1. More than half of you have turned that in. I'm preaching to the choir pretty much here, but test 2, I only see about 5. That's about 1/3 of them have turned in test 2. And as was asked just a few minutes ago, we have test 3 coming up pretty soon. I have it made out. I don't think I have the copies made because we've still got another section to go after this one. Now, any questions? Anything we've done so far? All right. Now, where we were last time, make sure I've got my mark right. In Chapter 3, Application of Differentiation, 3.6, a summary of curve sketching, and we were just about to get started on example 5, which is not on the slide set, but let me get my pen set up. There we go. It's, you can see larsoncalculus.com, free website for an interactive version of this type of an example. So even though it's not on the slide set, you can see them discuss it at pretty deep levels. Okay? It says analyze and sketch the graph of this function. F of x is equal to x to the 4th minus 12x cubed plus 48x squared minus 64x. Okay. Now, it says analyze and sketch the graph of that. Let's start with the analysis. What can you tell me about that function just looking at it? Okay? It's what? It's a polynomial function, which tells you what about the domain? All real numbers. Now, doesn't tell you much about the range. What tells you a little bit about the range? Not totally, but something about it.
Does it have to do with 64 or?
Have to do with what?
Does it have to do with 64? 64x?
Not really, okay? Look at the other end.
It's a parabola.
Okay, it's not a parabola. In the long run, it acts sort of like one. I think what you're getting at is pretty close. Look at the leading term. Okay, what do you notice about that? Even power, exactly. And what do even powers do? They act like parabolas. They either go up and up or down and down in the long run. What does this one do? Okay? Because it's a positive leading term, it has to be going up. You're absolutely right. Just think. Give a big number for x. Doesn't have to be very big. Like 10. That's not very big. 10 to the fourth power is? Yeah, exactly. It's 10,000. So when you go over just 10, you're already at 10,000 on the y, or somewhere up in that. And same thing here. Negative 10 also is 10,000 because it's an even power. So it's on the up and up. Okay. Now, what that tells you about the range is it's unlimited positively, but it's limited negatively. We don't know how far down it'll go. Now, maybe that negative 64x will contribute. I think more likely the negative 12x cubed will contribute. But the key thing is that there's some bottom here. Because the end's going up and up, that means there's some minimum value it's never going to get below. So you got an idea what it looks like. And that idea about, in the long run, it looks sort of like a parabola going up and up. That's not a bad way to think about it. Okay. So, we've talked about domain, all real numbers, range, all real positive numbers, somewhere either small negative or positive numbers or negative numbers, somewhere down there you have a bottom, okay, a minimum, okay? Let's go on. What else can you tell me about it? Just looking at it. What would be one thing as you glance at it and think, ooh, we need to do that?
Cancel out all the x's.
Say again?
Factor out all the x's.
Okay, factor out whatever you can, and all you can do right at first is 1x, because that term only has 1. So what do you have left?
X cubed.
X cubed.
Minus 4x squared.
Okay.
4x.
Say again?
Plus 4x.
Plus 48x.
48x.
Okay, right?
Minus 64.
Minus 64. All right. We factored it. Now that tells us one more piece of information. What's that? Okay, here's Will, if I can find you. There you are. All right. Again, top part of the alphabet is doing quite well. Middle part has somebody here. The bottom part, nobody yet. Okay. So what does this tell you? We factored out an x. What does that tell you? Why would you factor anyway? What's the purpose of factoring? Simplifying is certainly one, but really it's going to help you find something. What does it help you find? The what? What did you say?
You say axis of symmetry as x. Axis of symmetry?
This one's going to be tough to find an axis of symmetry. If it was a parabola, for sure, but this is a quartic function, and with all those varying coefficients in there, I doubt if it's going to have one.
The x.
The what?
The x.
What about x? Say again?
I can't hear.
You said reflection.
One more time.
Reflection.
Said points of reflection, I think.
Okay. Is that what you said? Okay. We're going to get that by doing what? Points of inflection come from second derivatives. Okay? We're not there yet. We're just looking at the function. We're going to get there, though. Absolutely. But what does factoring do for us? give us our zeros of the function, right? In other words, the x-intercept, where the function crosses the x-axis, the zeros of the function, where y is equal to 0. And we know one already, and where is that? X equals 0, okay? Now that tells us two other things, okay? One other thing. One is a 0 or an x-intercept. What's the y value there? X equals 0, what's your y? 0. That also gives you your y-intercept. Where x is 0 gives you your y-intercept. Where y is 0 gives you your x-intercept. 0, 0 is both, or one of the x-intercepts. Now what we've got to do is see if we can figure out what to do with the rest of that. Okay? Now, anything come to mind that we might be able to do with that? At least give it a shot. Looks like there is a slim chance you might be able to factor that. What is one of our factoring techniques? When you have 4 terms, even number of terms? Grouping. Let's try factoring by grouping. So what I'm going to do is group these two and those two together. Now, that's not a factorization, that's just grouping. Don't forget your x, that's out there. And what can you do with the first group? Factor out a what? X squared. And what does that leave you with? X minus 12. Okay. And in the second group? Anything? So you can go a little bigger than 4. Say again, 8. Maybe a little bigger than 8. 16. And what does that leave you with? 3x minus 4. Factoring by grouping doesn't give us anything we can use. Good try, but it doesn't. If these two had turned out the same thing, factoring by grouping would be helpful. Didn't work this time. Sorry about that. Worth an effort, but no cigars this time. Okay? So that didn't work. All right. Now, there are other things we can do. Okay? It just depends on how much time you want to spend on this or get on to the next part. One of the things, let me get rid of those two. Since grouping didn't work, those, that one I needed to keep. Okay. All right. Now, if you flash back to your pre-calculus courses, you might recall that you can use something called, there's a couple things you can use. One that comes real quickly to mind is the Cart's rule of signs. Remember how that goes? What do you count? Number of sign changes. Here you have 1, 2, 3. What does that tell you? You could have 3 or 1. You have to subtract 2 from it. 3 or 1 positive real zeros for that function. That's what it tells you. 3 or 1 positive real zeros. Doesn't tell you what they are, but you do have them. And the Cart's rule of signs says then do f of negative x, okay, which would leave that would make that negative, that would leave this negative, that would make that negative, and that would leave that negative. You have no sign changes there, so you have absolutely no negative real zeros. And Daniel's here.
The square root wouldn't make it the square wouldn't make it a positive.
Okay? If you put a negative x in here, then this becomes negative x cubed, right?
Yes.
Okay. Put a negative x in here, and what do you get?
Positive.
Positive. So negative times positive is still negative, right? Okay, so that's negative, that's negative. Put a negative in here, That becomes a negative. And then there's nothing to put in there, it stays negative. So all those, no sign changes when you put a negative x in there, meaning you have absolutely none, 0 negative real roots for that cubic polynomial. None. So when we start looking, don't look negative. Only look positive. You know you got at least 1. We're told that, either 3 or 1. But we know we have no negatives. Okay? The next thing we could do, and we don't have to do this, but we can if you need it as a review, is do the rational zeros test. Remember how that goes? You look at the last term, do all the factorizations of that. Okay? Plus or minus 1, plus or minus 2, no 3, plus or minus 4, no 5, no 6, no 7, plus or minus 8, no 9, no 10, no 11, no 12. Yeah, no 12. Is it? Yeah. 16 would be the next one. 32 would be the next one. 64 would be the last one. All those possible rational zeros. Okay? And here's Noah. All right. Oh, I forgot to mark the code. I saw it come in. Anyone else sneak in while I wasn't looking? Okay. So, you could do your rational zeros test. Remember? The possible factors here, plus or minus 1, 2, 4, 8, 16, 32, and 64. But guess what? Don't mess with the minuses. You know we can't have any negative zeros, okay? So only the positives. And then your denominator of that rational zeros is all the possible factors of your leading coefficient. 1. So there you have your possibilities. So then you can start going through each of those. Synthetic division works really, really nicely here, and checking to see if any of those are zeros. Okay? And that's certainly something you can do. Okay? Now, I guess we need to do it because they came up with a factorization just out of the blue. So let's do that. So our possible rational zeros were plus or plus. Okay. I'm just going to leave off the signs completely. Okay. Were 1, 2, 4, 8, 16, 32, and 64. Okay? Now the easiest one of those to check is which? 1. And if x is equal to 1, all you do is add your coefficients, right? Because that would be a 1, that would be a 1, that would be a 1. I mean, everything's a 1. So these two add to negative 76, that only adds a positive 49. Not a 0. Let's do the next one, 2. Now this time, let's do synthetic division. Okay, 2 on the outside, and what do we put on the inside? Remind me how to do synthetic division. Help me. Okay, 1, negative 12, 48, negative 64. And then you skip a line, draw a line, bring down the 1. Multiply and you get 2. Add you get negative 10. Multiply you get negative 20. Add you get 28. Multiply you get 56. Not 64, right? So not going to work. 2 isn't going to do us any good. So we erase those. Okay? But we can try the next one. 4. Let's see what we get if we do a 4. I brought down the 1, then you get a 4, negative 8, help me, negative 32, 16. 64. Ding, 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 ding. We have a winner. Okay? X equal 4 is a 0. Now, if x equal 4 is a 0, what is your factor? If x equal 4 is a 0, and we already had determined that x equal 1, x equals 0 is a 0. If x equals 4 is a factor, is a 0, what is your factor? X minus 4. Right. Okay? Now we can continue. Except we're down to a quadratic here. So at this stage, don't mess around with synthetic division again. Can we factor that? Or what does that represent? Get it back into a quadratic. X squared minus 8x plus 16. Can we factor that? How? Times x minus 4. Hey, looks like we got a whole string of those. That's 3 factors of x minus 4. Now that's where the book went to right there. They said you can factor this as that. How? Okay. I can't look at that and say, oh, I know, that's x minus 4 cubed, But here's how you do it. Okay, using this rational zeros test. This is one way to do it anyway. Go through your possible factors and then work them out. So what does that tell you? If you got the factorization here, why did we do that? To find the zeros. And we already knew 1 0 was 0. The 1 0 was 4. But yet that's a repeated 0. That's x equal 4, that's x equal 4, that's x equal 4, okay? So we have a repeated 0, multiplicity of 3 for x equal 4, okay? So we know our 2 zeros. Now it said, analyze the function, that's what we're doing, but it also says sketch the graph. So let's start this graph, the sketch of our graph here. We know x equals 0 is a 0, and x equal 4. 1, 2, 3, 4. That's probably not going to work out well, but I'm going to do it. There's a 0. In fact, that's a multiple 0. Now, since the multiplicity of 3, what can you tell me about that? Okay. Time out again. What we said at the very beginning. We know this function's going up and up. Okay? Because it's a even degree positive coefficient. It's got to be going up. Okay? And there we got a 0, so I can almost guarantee you that's coming down like this. Right? It's going to do something down here, but then what does it do here? At this 0 here. So this is a multiplicity of 3. Yeah, it's going to cross the x-axis. It's going to linger there a while because it's a multiplicity, but it's got to cross. If that was an even multiplicity, then it's going to come up and hang around and then go back the same direction. Or come down, hang around and go back the same direction. But since it's an odd multiplicity, it's going to come up and up. And since we know it's got to go up eventually, then it has to cross. And it had to be coming down. So somewhere in here is the rest of our activity. Yes?
Before we did the rest of the zeros test, you said Luke just gave us x times x minus 4 to the third power. That's just one of the answers. And we got something different to say with our going through the rest of the zeros test. So.
Oh, yeah, you got exactly that. X equal 4, so the factor was x minus 4. And then when we factored this, we got 2 more x minus 4s, so we got exactly the same thing they got.
I get the x minus 4 part, but I was wondering what about the cube part and the x in front of it. But that's
the what?
The x in front of it, of the problem, and the cube.
Okay, the x here, we already determined that's x equals 0 that factored out.
Okay.
Okay, then we were left with a cube that gave us potentially 3 more zeros.
Right.
We got them, but they're all the same number. X equal 4, x equal 4, and x equal 4. Okay, so that's why you only have 1 more out there. Okay, so we already know something about this. Coming down here, doing some mess here, hanging around here, but going back up there. We already have a general idea what the tip of this graph is going to be. So let's carry it further. This is about all that pre-calculus told you to do. So now what do we consider doing? Taking a derivative. It sounds like a winner to me. So f prime of x is equal to what? This is so aggravating. There it is. Okay. What's f prime of x? Anyone help me? 4x cubed minus 36x squared plus 96x minus 64. Now, why would we take a first derivative anyway? Second? Okay, that's certainly one thing. Maybe a little more important than that. Your. Okay. Your critical values. That's what the main thing. And that does lead to increasing, decreasing, but the main thing you get for your critical values. Where, what defines or determines what your critical values are. No, that's not second. That's the points of inflection. Okay? Critical values are first derivative. How do you tell? What about the first derivative tells you anything about critical values? Two tests. We do this every class, it seems like. Where the first derivative is? Zero or undefined. Now, is that undefined anywhere? No, it's a polynomial function. Polynomial functions are defined everywhere. We already said all real numbers, and that's still a polynomial. So now we're only interested in where the first derivative is zero. The function where s equals 0, that gives you your x-intercepts. Okay? Where your first derivative is equal 0, that's going to give your critical values. Okay? So we set this equal to 0. And what's the first thing you might note you can do to it? Make life simpler. Factor out of 4. So that would be 4 times x cubed
minus
9 x squared.
Wait, is x squared? Or was that? Yeah, it's not x squared, it's not x.
That's squared, yeah.
Wait, no, it's not taking derivatives.
What's that? Have I done something wrong?
No, you did it right. I was thinking about derivatives. You could,
Plus. Okay, does someone else have something? It's okay? Or not? Was there any objection? Okay. Okay. Next. 4 will go into 9 twice. With 1 left over, 4 will go into 16 4 times. 24x. Right? Minus 16. And that equals 0. Okay? Now this is to get our critical values. Well, you know x can't be 0, so just divide that out. 4 can't be 0, divide it out. Okay? Now, I don't think it's worth trying to do factoring by grouping. I can tell you that's not going to work here either. So to find these zeros, we have to go back to what we did before. Now, since we've already done that, let me clear this part of the thing, okay? Okay, we've already done all this stuff, so we don't need this anymore. We wrote down our results here. I just need the room, okay? Okay. Now, the critical values are where this is equal to 0. Okay? Now, what I did, just like we were doing before, how do we find the zeros of that function? Well, we can do the Clark's rule of science. How many possible zeros do we have here? Positive zeros? 1, 2, 3. Or 1. Okay? And by the way, before, we said we had 3 or 1 positive zeros. You can either count this as 3 because it's 1, 2, 3, or count it as 1. Either way you want to do it. So yeah, that works for us. No negative zeros. We already determined that. And if you do f of negative x, that would make this negative, keeps that negative, make that negative, keeps that negative. No real zeros here either. So none of our critical values are going to be negative. You could have 1 or 3, 3 or 1 possible critical values here. So let's see what we get. Now, the next thing we did was rational zeros test. Take the last term. Don't mess with the negatives. You already know there aren't any negatives. So the possible factorizations of 16 are 1, 2, 4, 8, and 16 divided by 1. That's just, okay. So those are our possible zeros. Easy one to check is 1. You just add the coefficients. Negative coefficients add to
Plus 27.
Second?
Negative coefficients add to 27.
Okay, one more time. Not 27. 9 and 16.
3.
9 and 16.
What are you looking for?
Adding them up. Add those two negative coefficients. Yeah, not that.
20.
25. Negative 25. Positive coefficients. Positive 25. We have a winner right there. X equal 1 is going to be a critical value for that problem, because x equal 1 makes the first derivative equal to 0. Right? Okay. So, let's do that and see if we have any others. Since we know 1 works, we can do our synthetic division with 1. Okay? And now the coefficients are 1, negative 9, 24, and negative 16. Right? Skip a line, draw a line. Bring down the 1. 1 times 1 is 1. Negative, no. Negative 8, okay. Negative 8. Second? 16. Second 16. 0. Ding, ding, ding. We have another winner, right? So we have a critical value at x equal 1, okay? So let's call it c equal 1. Critical value, c equal 1. Okay. Now, what do we have left here? What else do we have? Yes, and how does it factor? X minus 4 times x minus 4. So x equal 4 is also a critical value. Okay? Now, we kind of knew that anyway, because I already said the function's going to come up here and linger around here because that was a triple 0, right? So lingering there, sure enough, is going to make a horizontal tangent. Okay? So sure enough, I'm not surprised. Okay? Now the question is, c equal 1 over here. We know it's coming down here, it's going back up here. So this, I would say, almost has to be a minimum. We haven't checked it yet, but I'm going to guess c equal 1 is a minimum. Okay? The C equal 4, though, that's also a critical value. And it's a double critical value. C equal 4, multiplicity of 2 if you wanted to call it that. We don't know what it's doing there, okay? I have a suspicion, because I know it's coming from down here, hanging around here, and then crossing. So guess what? I'm going to predict that's a point of inflection, okay? Not a max or a min. This, I'm predicting, has to be a minimum, okay? That's my prediction. Let's carry it a little further to see if we can verify that. So once we've taken the first derivative, that gives us our critical values that tell you where our extreme values are, max and min. We think we've got one, but let's go on, and what's the next thing we do? Second derivative. So f double prime of x is going to be what?
12x squared.
Okay, we can go back and include that. We surely can. 12x squared. Negative 72x plus 96. Done. And what do we do with that second derivative? Okay, how do we do that? Yes, either set it equal to 0 or it doesn't exist. Anywhere that doesn't exist? No, it exists everywhere. It's still a polynomial. So we set it equal to 0. Okay? And take the 12 out. Okay? So what does that leave us with? X squared minus 6x plus 8. Okay? And what can we do with that? Factor out the 12. Okay. Say again? And how does that factor?
That would be negative 4, x minus 4, x minus 2.
X minus 4 times x minus 2 equals 0. And what does that tell you about your two? X equal 4 and x equal 2. Now these are potential, not guaranteed, but potential what? These 2 points. Inflection points. Okay? Now, x equal 4, we've dealt with that 3 times already. It's a 0, it's the first derivative of the horizontal tangent line, and sure enough, that's going to be, we're guessing, an inflection. We can check that out for sure. X equal 2, though, pretty sure that's going to be an inflection point as well. Okay? Now, all right. I sort of got carried away here. Okay? Let's go back and on our critical values, let's find out what the function value is at x or c equal 1. So go back to your function, and when c is equal to 1, we did that, remember? We did that when we were checking to see if that was a 0. This added up to negative 76. This was 49, and negative 76 plus 49 is going to be 20. Okay. 27. Negative 27. Sound right? Okay, let me see what they got. Yes, minus 27. Okay, so x equal 1, okay, gonna have to do some pretty major scaling here, okay? We did 1s on the x-axis like that. On the y-axis, we're going to have to do 10, minus 20, minus 30, okay? So at 1, we're down here at minus 27, okay? And that, okay. How can you convince me that's a minimum? I think it's got to be. You need to convince me. How do we know that x equal 1, y is equal to negative 27, that that's going to be a minimum?
We'll see our first point starts at 0, 0, and then it goes down to...
Okay, yeah, that was my argument. here's how you can prove it beyond the shadow of a doubt. Okay? Take that second derivative, right there it is, okay? And I'm going to leave it in this form. Yeah, this form probably. And plug in a 1. And what do you get then? You plug in a 1 for x. X equals 1. C is equal 1. 3. You get 8 minus
2.
2, okay. Okay. No, it's not. That's 3. 9 minus is 3. Times 12 is still positive. What does a positive second derivative tell you? Opening upward. So therefore that has to be a minimum. Okay. Now, let's do the same thing with x equals 4. Or c, well, x equals 4 here. No, c is equal 4, sorry. Same thing. It's that point right there. Okay? We already know what's going to happen. You plug in x equals 4, and you're going to get 0. Right? Well, wait. Yeah, you will. Because we did that at the very beginning. That's a 0 for the function. So that doesn't tell you anything. So now we have to look to the left and to the right. So let's plug in x equals 3 here. And do that. Second derivative at x equals 3.
It's 1.
Okay, this will be 9 minus 18 plus 8. 9 and 8 is 17 minus 18. What's that?
1
is negative 1. No, you're right. Yeah, I'm sorry.
No, it's negative 1.
Negative 1. Okay, I thought so. Negative 1. Okay, so that means what's your second derivative on this side?
It's concave down.
Concave down. Okay, let's go to the right at 5, and what do we get? 25.
It's 30.
That would be a minus 5.
Plus 8, so it's plus 3.
Positive on this side. So negative on this side, positive on that side. Yes, that's the point of inflection. Because your second derivative, your concavity changes at that point. Okay? Concave up here. Okay? Now, we've already proven the next one. Remember, x equals 2 was your next one that we thought was going to be a point of inflection. Let's go and plug in the 2 here too and see what we get. X equals 2, what do we get?
2.
Second?
In the FX?
Yeah, in the f of x. Second, 16.
96.
It's a negative 96, right?
Negative 96.
Okay, subtract 16, so that's a negative 80, right?
Plus.
Big number, right?
192.
Okay, so negative 80 plus 192 is 112, or something around there. And then this is 128, negative 128. So it looks like to me, yes, negative somewhere down here. So that value here is negative, not nearly as negative as this one is, but it's negative down here. I didn't follow it. Use your calculator, see what it comes up to. But that's your second inflection point. And we know that's an inflection point because we know it's concave up here. We already tested here, it's concave down here. That point has to be an inflection point.
So I got a question. When we get those inflection points, like x equals 4 and x equals 2, you plug that in the second column, or do we just plug in the original function?
Okay, when you're getting the point to plot like we did here, you plug it in here. Because the point comes from x, y. This is y. Okay, so that's what you're doing, is finding the place to plot it. I just didn't carry all that out in my head, but it's somewhere up here is, I don't know where. Did they put it in here? well, they didn't. Yeah, there it is, negative 16. Okay, so negative 16 is somewhere about here. Okay, so there are the points we know. Okay, so we know it's coming downhill here. It has a minimum here. It has an inflection point here. It hangs around here, has another inflection point, and goes up. Now, they did it a couple more points. They did a point here so you can tell exactly where it was, like negative 1. There's no reason to do anything else in here. You've got everything you need to know here, and you might want to do one at 5. We did a concavity at 5, but you could actually find the point at 5 to see what that is. I don't. That to me is fine enough. There's the graph of the function. Okay? It's going up and up, just like we knew from the very beginning. We found our 2 zeros. This one here was a multiplicity of 3. That's a multiplicity of 1. This just crosses right dead away. This one comes around and hangs around. I didn't draw that very well. It comes up here and hangs around here and then finally goes up, so that gives you a horizontal tangent line, which we knew from a critical value. But it's not a max or min because it's an inflection point. Here's the other kind of inflection point where it changes concavity from concave up to concave down there. That's the other kind. This is concave down to concave up. Another inflection point. This is also horizontal tangent. This one doesn't have horizontal tangent. There we have it. We have analyzed the graph. We have sketched the graph. We know more about it than you ever cared to know, right? That's how you do it. Right? Any questions? Make sense? All right. They do a few more things here, but a relative minimum, in fact, an absolute minimum at x equal 1. F of x is negative 27. That's your absolute minimum. Then they did the analysis of decreasing and concave up and that kind of stuff just by plugging those test values in, okay? And then we have where it's decreasing. It's decreasing from negative infinity all the way down to x equal 1. It's increasing from x equal 1 to positive infinity. Never stops increasing there, okay? Concave up here all the way to here, concave down to here, and concave up again there. We got that. And critical values were this one, horizontal tangent line, that one, horizontal tangent line. This is a minimum, that's the point of inflection. There's the point of inflection. So you got all the details you need. So, any question? Yeah.
Have you ever, it's kind of a question, but it's off topic. Have you ever used the number line to plot like your critical points and like inflection points?
Okay, tell me what you mean by that.
Like you use the number line and like basically you plot like 2 and 4 on a number line because we got it on the F double line. And like you look for numbers to the like right of it and you plug it in. Like,
do what now? The last part. Okay. In other words, you
get a number line and like you plot 2 and 4, right?
Right.
And so basically to see where it's like concave up or concave down, let's say you plug in 1, and if it's a positive number, you put a plus to the left of 2.
Yeah. That's kind of what I was doing without writing it down. That's what I did here when we did test points. I didn't do a negative 1, but I said you could. And you do the function there, you do the first derivative there, you do the second derivative there. And that tells you what it's doing. Yeah, that's the book's big old table does that. But I just looked at this and said it's concave up everywhere from there to here, okay? That's the only place it changes concavity, okay? I could have looked at those points, the number line, and confirmed that. I probably should have. I was just too lazy to do it.
I was just wondering if
Yeah.
you do that.
Yeah, that's a great way to go. It is. You use your critical value, you use your zeros, your critical values, and your second derivative values, okay? And those are the minimum. And then you do a test interval, something to the left, something in between. So yeah, every one of those you do. But if you can already tell what's going on, yeah, it seems a little redundant. That's the only reason I don't do that formally, is after a while I can tell what's going on. There's a zero, there's a zero, there's a zero. We already established that. We knew this is a multiplicity of 3. So we knew what it was going to do. It's got to cross there, okay? And knowing it's going to cross there, I already know that's going to be an inflection point, but we went on to verify it was, okay? So yeah, we did a lot of that, and then there's no way but what this is, I didn't have to check a point here or a point there. I did do this second derivative here, concave up, that's how we do it. So I did do that, but I didn't do it as organized or as you were talking about on the number line. But yeah, we did sort of do that same thing. We did the values, we did the first derivative, we did the second derivative, and we did test values. So, but yeah, that's a good idea to do. That shows the whole picture. And that's what their table in the book does. So that's one reason they do it. Okay? I should do it. I'm sorry. I'm just too lazy. Okay. All right. So that's example 5. Let's move to example 6. Any questions on 5 before we leave it? All right. Here's example 6. I would say I'll do what you requested, but I'm not sure I will, but let's try it. Analyze and sketch the graph of this function. Alpha of x is equal to cosine x over 1 plus sine x. Okay. Oh, joy. Okay. Now, it says analyze and sketch. So this, as opposed to the previous one, which was a polynomial function, first thing we said, polynomial function defined everywhere. Is this a polynomial function? Nowhere close, okay? This actually isn't even a rational function, though it does sort of act like a rational function. A rational function, by definition, is a ratio of 2 polynomials. This is a ratio of 2 trig functions, but it's still a ratio, so we can use some of those same techniques that we use to evaluate that. So what are some things we consider when we're looking at rational-like functions? What are the things we look for? Some are the same as we did before.
Trig identities.
Okay, yeah, we didn't do trig identities before, but if there was one in there, I would certainly use it. I don't see one right now. But there are certainly trig functions. Okay, we are certainly going to do that in a minute, but let's just first look at the picture of things we can do without even taking a derivative. What were the things we did on the last one? Yes, find the zero of that function. Where is that function equal to 0? Okay, I think not, but it's 0 only where the numerator is 0, right? That's the only way a fraction can be a 0 if the numerator is 0, right? Okay, yeah. If you think in terms of degrees, that's 90. If you think in terms of radians, which you should be thinking in, what is that? Pi over 2. Okay, in fact, all of your half pi's are going to be zeros. Because guess what? These are trig functions. They're periodic functions. Sine and cosine are both periodic. Period of 2 pi. So we know it's going to be repeating itself. Okay, so I'm going to go on and start by plotting at least that. Okay, we said at pi halves, 3 halves pi, 5 halves pi, we have zeros every one of those. Okay? And back here at minus pi halves, minus 3 halves pi, minus 5 halves pi. I don't need all those, I'm just putting them in because I can. So you got a 0 here, a 0 there, a 0 there, a 0 there, a 0 there. Every half pi is a 0. Okay? So we got our zeros. Now we didn't take a first derivative to find those, but no, we didn't need to. Those are just where the numerator is 0. Okay. Now, what are other things we deal with in rational type problems? This isn't a rational function, but rational-like functions. What's the other thing we deal with? Anything? Okay. Rest of class, come in please. Okay. Okay. Anytime you have a variable in the denominator, what do you worry about? Second, the denominator becoming 0. So we need to investigate that. We found there are zeros up there. We need to figure out whether the denominator is equal to 0. Okay? And where would that be? Where? Negative pi. I think you're right there. Let's see. No, I don't think you're right. Oh, wait. No. It's 1 plus sine x cannot equal 0. So that means sine x cannot equal negative 1. Right? Right? Subtract 1 from both sides. And where is sine x equal negative 1? Sine starts at 0, goes up to 1 at pi halves, 0 at pi, negative, or 3 halves pi. So this now is not a 0 anymore. That's a vertical asymptote. And this one's a vertical asymptote. Okay? Because there you got your denominator equal to 0. You can't have a denominator equal to 0. So we do have, no, I'm sorry, I did that wrong. At negative, I think it can. Yeah, at negative pi half, not 3 halves pi. Sorry, I messed that one up. Okay. Why is this not erasing? Okay. At negative 3 halves pi. Not negative pi halves. I keep saying 3 halves pi. Right there it can't be. So that's another vertical asymptote. Why? Because at negative pi halves, sine is negative 1, and sine can't be negative 1. Okay. So we have a 0 here. Okay. And then it's going to repeat itself. You're going to have another 0 here, another vertical asymptote here. Another 0 here, another vertical asymptote there. Okay, it's just going to keep repeating itself. All right. So now we found the zeros. We found our vertical asymptotes. Now, this one we didn't do before because we actually backed into it and had it done already. Another really easy point usually to get is we did our x-intercepts, found out half of them are wrong because they were vertical asymptotes, but what intercept have we not dealt with? The what? We found the x-intercepts. The y-intercept. And where is y-intercept? What's always true about a y-intercept? It crosses the y-axis. What's true about every point on the y-axis? Yes. Name this point right here. At least one of the coordinates. Okay, it has two coordinates, x and y. Can you give me the x coordinate button? 0. And that one's 0, that one's 0, that one's 0. So if x equals 0, plug in a 0. What do you get when cosine of 0? 1. Sine of 0? 0. And 1 over 1 plus 0? 1. So, here is our y-intercept. X equal 1. I mean, y is equal to 1. Okay? Now, we have 2 points in here. And by the way, that 1's going to repeat itself here and here because, no, am I right? No, I'm in the wrong place. Here, I'm sorry. Not there. Okay, sorry about that. It repeats itself every period. So, not there, but there. Okay. All right. All right. But that's beside the point. I'm only interested in one period. All right. Vertical asymptotes. I know it's got to approach that. Let's now, we've done what we can with algebra. Zeros, y-intercepts, vertical asymptotes. I think we've just about extinguished what we can do. Okay? So now we go to what's this course? Calculus. Okay, we've used the algebra part. Let's now use our calculus to let us know some other stuff. I'm going to erase this because we've already established that and that. Okay. So now what we've got to do, and I can tell that Nolan's been chomping at the bit to do this one. Because you get to use the quotient rule. Yes, okay. And how does that go?
Okay, 1 plus sine x.
Okay, lobe, 1 plus sine x.
Times negative sine.
Negative sine. Minus.
1, it'll just be cosine.
Cosine x.
Times cosine x.
Say that one more time.
Times cosine x.
Times cosine x. So that'll make it cosine squared x, right? Okay. So let's see if we can clean that up a little bit. That would be a minus sine x minus sine squared x minus cosine squared x. Oh, I forgot to put it over the denominator. What's your denominator?
It's going to be
1 plus sine x squared. Okay. Now, that's done. I shouldn't have erased everything I did. Let's do up here. X cannot equal. You know, remember what we did? X cannot equal. It no, it's your 3 halves pi, and then that's plus 2n pi. Okay, any of those multiples, 2 pi multiples of that. Okay, so I've already marked them there, but I wanted to remind ourselves there. Okay, now so there's your first root. What? Okay, can we clean that up just a little bit more, especially that numerator? Minus sine x minus, factor out a minus sign from those two, and what do you get? Sine. See what I'm doing? Factor out a minus sign from the last two terms there. Sine squared x plus cosine squared x. Because what in the world is that? What's sine squared x? What's cosine squared x? DeMarcus was wanting this earlier. He got it. Huh? It is 1, exactly. Okay, so let's see if we can clean that up a little bit more. That will be a minus sine x minus 1, right? Over 1 plus sine x squared, right? But if you factor out a minus 1, that would be a minus sine x plus 1 over sine, I'm changing the order, x plus 1 squared. Well, guess what? You wind up with minus 1 over sine x plus 1. Or 1 plus sine x. I don't care how you write it too much. Okay? There's your first derivative. Right there. Now, what are we interested in? Why do we take a first derivative anyway? Second? Yes, you want to find your critical values. And where are those critical values? Either whether it's 0 or undefined. Now, is that first derivative right there, negative 1 over sine x plus 1, is that ever 0? No, because 1 is never 0. Negative 1 is never 0. Only way you can have a fraction form equal 0 is that numerator be 0. It can't be. So this has no zeros, no places where the first derivative is 0. Is there any place where that first derivative is undefined? It's the same as where the function is undefined. And you don't consider those. So this has no critical values, which means it's never going to change its direction. Right? The critical value is where potentially it changes its direction. It's not going to happen. Okay? Except if those are asymptotes, then we don't even count those. Okay? So, I can tell you right now, since it doesn't change its direction, there's no place where the first derivative is 0, that means I can tell you just looking at this, since 1, 0, 1 is on there and pi half 0 is on there, it has to be doing this number right here. And I'll bet you a bottom dollar that at x equal pi, this is pi here, you're going to be, the function value is going to be negative 1. Anyone want to take my bet? Okay? I can almost guarantee you that's going to be the case. Let's see. Plug in x equal pi here. Cosine of pi is? Negative 1. And 1, what's sine of pi? 0. Negative 1 over 1, 0 over 1, negative 1. I guaranteed you that's going to be there. So this has no critical values. No places where you have a max or min. No place you have a local extrema. None. Okay? Now, and your first derivative is always between negative pi halves and pi halves is always negative. Because sine of x plus 1, sine of x never gets outside plus or minus 1. So when it's plus 1, negative 1 half. When it's minus 1, you're undefined. So guess what? That's always negative. Always negative. Sure enough, that's going downhill the whole way. Okay, so that's what your first derivative tells you. Let's do the second derivative. With that being your first derivative, what would be your second derivative? Now, what I'm going to do here, if it's okay, I'm going to erase a lot of my work here because I just don't have room to have it hanging around here any longer. So I'm going to erase all this. Okay. And all this. Whoa, I erased too much. Okay, erase that. Oops, I erased too much again. Okay, and I think I can erase this. All right. Now, there's my first derivative right there. Okay? How are we going to get your second derivative? How are you going to do it? Anyone help me? Anyone? I'm hanging here. No one's going to help me.
I'm not sure how you started off with.
Say again?
I was saying I'm not sure how you're going to start off with.
Okay. You have two choices. One is the quotient rule again. I figured he was going to say that, but he never would. Or I would be a bit more inclined to do this as negative 1 plus sine x. I'm going to go back to that term, to the minus 1. Because the quotient rule, when you take the derivative of the numerator, it's going to be 0. So you're just going to wind up with one thing. So let's take the derivative of that. And what would that be? Pretty easy to do, isn't it? Power rule. Help me. Take the derivative of that. Anybody? 1, okay. 1 times 1 plus sine x to the negative 2 times say again?
I was saying times confused.
Because you got to do chain rule.
It's the first times the derivative of the second.
Okay, wait. Okay, we're just doing a power rule here. Huh?
Would it just be cosine?
Cosine, exactly, times cosine x. Okay? Because what you do here is a power rule to start with. Negative 1 times negative 1 is positive. This thing to the minus 1, so it was minus 1, subtract 1 more, it's minus 2. Now the chain rule part, derivative of the inside, derivative of sine is cosine. Okay. Now, let's rewrite that slightly as cosine x over 1 plus sine x squared. Okay? Now, why did we take a second derivative anyway?
Find the points of inflection.
Second?
Find the points of inflection.
Points of inflection, and where did those occur?
Where there's a
Second?
When you just
No,
set
change.
don't you set it equal to 0 before you find it?
Yes, okay. It's either where the second derivative is equal to 0 or
Undefined.
where it doesn't exist. Now, the only place it doesn't exist is the same place that the function didn't exist, so don't worry about those. It's not ever going to be there, okay? So how do you make that second derivative equal to 0? There's the second derivative. Where is that equal to 0? Huh?
Negative 1. So sine.
Okay. Okay. Not the denominator. Okay. Okay. We already messed with the denominator. We know those can't be at the first class. They can't. So don't even mess with those. The function's not defined there, so the first derivative is not defined there, the second derivative is not defined there, nothing's defined at those vertical asymptotes. So forget about that. But you said where it's equal to 0. Where is that equal to 0?
Yeah, pi
Okay.
or 0.
This expression right here. That expression, where is that equal to 0? No, just a fractional thing. Where is that equal to 0? When the numerator is 0, right? The only place a fractional form can be 0 if the numerator is 0, right? If the numerator is anything other than 0, you'll never have that thing to be 0. So all we're interested in is where cosine x is equal to 0. Where is that?
1. Not 1.
Pi is -1. Cosine. Cosine starts at 1, 0 at pi halves, -1 in pi, right? So pi halves. That's where you have the second derivative equal to 0. And guess what? There it is. Notice here, this function is just the way I graphed it. In fact, it has to be graphed that way. Concave up there, concave down here. That's your point of reflection. Pi halves. Okay? Plug it in and see. I think you'll find that's the case. Because x equals 0, that's going to be 1 over a positive number, 1. So that's going to be positive here. X equals pi, that's going to be -1 over a positive number. So this is concave down here, concave up there. Has to be your point of inflection there. And that's your only point of inflection. Right? Oh, well, I mean, it repeats this pattern every time, so you're going to have the same curve here, the same curve there, same curve infinite number of times, but just between -pi halves and 3/2 pi, in one period, you're going to have only that one point of inflection. 1, 0, no critical values, and 1 point of inflection. Okay? Now, I didn't draw mine as pretty as they did in the book. Forgive me. I didn't know what I was doing. But there's what your graph looks like. Okay. Any questions? All right. Homework exercises 3.6. Do either 5 or 7 or both. I would do all 4 of those, 5 through 8. The answers are in the back for 5 and 7. Okay, and they're also at calcchat.com. Then do any of the odds, 9 through 35. They're all at CalcChat. 33 is at CalcView. Do any of the odds 37 to 43. They're all at CalcChat. 37 is at CalcView. Do any of the odds 45 to 49. They're all at CalcChat. Do 51. It's at CalcChat. Do either 53 or 55 or both. They're both at CalcChat. 53 is at CalcView. Do 57. And if you want to look at 59 through 63, knock yourself out. It's perfectly fine to do. Then do either 65 or 67 or both. They're both at CalcChat. Do 69. It's at CalcChat. Try to do at least one of the odds, maybe more than one. Any of the odds between 71 and 75. They're at CalcChat. Do 77. That's the only one sort of like that. Okay. Then you can think about doing 79 or 81. That's up to you. True false, 83 or 85 or both. Graphical reasoning, 87 or 89 or both. Slant asymptotes again, number 91. And then you can do an investigation of 93 if you choose. Okay. Now, I wish we had time to do optimization problems. Are any of you going into industrial engineering? You are.
Yeah.
Okay. You ought to look at section 3.7. So that's what a lot of industrial engineering does, is trying to optimize your production, okay, and that kind of stuff. That is a really important section for you, okay? So I would take a look at that. You're going to do it in later courses, and the engineers probably won't get into as much math as this does, but that, I wish we had time to do it, but we really don't. But that would be an important section for you, okay? Let's move on to 3.8. Sorry, we aren't going to get to do that one. All right, finally. Well, for some reason this says click to exit, and I've clicked and nothing is, there it goes. All right. All right, now, Nolan, do you want me to throw up here the, well, actually you have them, the PowerPoints for this. You have access to all these PowerPoints, I think. I believe I put 3.7 out there, but I could just flash them up on the YouTube video if you want them. Would that be beneficial? Okay, I'll try. I hadn't planned to. I'll try not to talk too much about them. That's hard for me to do, though. Okay. Now, these are going to be a lot more esoteric than what you're going to run into in real life. But, well, I thought it would open one of these days, but it just is having a hard time doing so. Here it comes, maybe finally. While we're waiting for this, do y'all feel like this is a decent breakdown? It's up to you, I don't care. Don't need one? We can keep going. I was just thinking, sitting here watching PowerPoint send bullets across, that's pretty exciting, but you know. Okay. Finally. Okay. This section, which you're not going to be responsible for in your test, is optimization problems. Okay, I won't ask you any of these, but because you may run into them, you will run into them. Solve the applied minimum and maximum problems. Applied minimum and maximum problems, one of the most common applications for calculus, involves determination of minimum and maximum values. Critical values, right? Okay. Manufacturer wants to design an open box having a square base and a surface area of 108 square inches, as shown here. What dimensions will produce this box with a maximum volume? Okay. Now, the key here, square base. Key here, open box. Key here, surface area of 108 square inches. Okay. Now, what you do, the surface area of this box, it has a base. Now, that's your variable, okay? One of the variables, x. And it's a square base, so it's x on this side, x on that side, okay? Now, you have another variable that's more variable, that's your height. You can make that anything you want to, but the base has to be square. So what's your surface area of this box? Okay. Well, the surface area of the base is at x squared, length times width. And because these x's are the same, all four of those are x's, then your sides of the box, it doesn't have a top. The sides of the box are x times h. And you have 1, 2, 3, 4 of those. So 4 times x plus h. And that total surface area needs to be 108 square inches. Okay? Now, what you want to do is maximize this S. Okay. Now, oh, I'm sorry, no. I'm sorry. The surface area is fixed. You want to maximize the volume. Well, what's the volume of the box? The volume of the box is length times width times height. So it's x squared h. Okay? That's what you're wanting to maximize. This is fixed. Okay? Now, here's the key. Your surface area is this. So you can solve this equation for h. Okay? Get h out of the picture. Okay? Or get h as a function of x's and other numbers. Okay? Then plug that h that you just derived into your volume. The volume of the box, that's what you're wanting to maximize, is x squared h. Okay? Now, that's your primary equation. That's what you're going to be taking the derivative of. That's what you're wanting to maximize. Okay? But before you do that, you need to get rid of the h. And that's why I said use the other formula, the surface area, to solve for h. This equation is called the primary equation because it gives the formula for the quantity to be optimized, volume. Okay? But you have to reduce from two variables to one. The surface area is that. We've already said that. That's your secondary equation. Use that equation to get h as a function of x and numbers, which you're going to do here, and they're taking their time to get there. There's how you get your h. H is equal to 108 minus x squared divided by 4a. In other words, solve this equation for h. Subtract x squared from both sides, 108 minus x squared, then divided by 4x. That gives you your h. Now this h moves into your primary equation, okay? And this one right here, instead of h, you put that. That makes it much uglier, okay? X squared times 108 minus x squared over 4x. Okay? Now.
The x squares cancel out?
What's that?
Does the x squares cancel out?
No. Okay. One x cancels out. This x can cancel one of these. You can't cancel that. You know, those are multiplied together. But you can divide this into that. So that gives you 108x minus x cubed over 4. Pull the 1/4 outside. Take a derivative of the volume. Okay? So that's going to be, and they actually divided the 108 by 4. You get 27x minus x cubed over 4. Okay? That's what you take your derivative of. And that will give you 27 minus 3/4 x squared, right? Okay. Here they're getting off onto the domain, which let's see. This thing right here, okay, number one, x is a dimension. It can't be negative, right? Okay. There's just certain values it can be. You certainly can't have this thing being negative, okay, because you can't have the 108 is the total minus x squared is the area of the base, so you certainly can't have that. So there's just certain limitations here. They call those constraints, by the way, okay, and here is your feasible domain. X has to be between 0 and 108. And guess what, folks? X is not going to be 0, okay? And x is not going to be the square root of 108. So I would say take out the equal signs there. That makes no sense. If you have no base, you don't have a box, okay? So we take a derivative of that, and that's what I was saying before, 27 minus 3/4 x squared, okay? on that interval, 0 to, now they put parentheses there, not brackets, okay? And you solve for, set that equal to 0, and solve for that 3. Okay, what they're going to do is move the 3x squared over 4 to one side, multiply by 4, that gives you 3x squared is equal to 108, divide by 3, and you get 36, and x squared plus or minus 6. Okay, guess what? The x is not going to be negative, is it? Well, we already said it's going to be between 0 and square root of 108. So throw away the minus sign. You're not going to have a box with a negative dimension, okay? So x equals 6 is your answer. Yeah, technically your minus 6 is a critical number, but it's not important here, okay? You do not need to consider negative 6 because it's outside the domain, okay? So x equals 6 will be your maximum volume for that box, okay? Now they're also going to evaluate the endpoints. That's ridiculous too, okay? Your box is not going to have a dimension of 0. It can't. It's not going to have any volume then. Your 108, that's not going to have any value either. X equals 6. That's it. So V is a maximum. X equals 6. The dimensions of the box are 6 inches by 6 inches by what's left? 3 inches. Now, I don't know. Oh, yeah, you go back and plug that into your H function, and you can figure out what the max is. So here's the guidelines for solving applied minimum and maximum problems. Identify all the given quantities, all the quantities to be determined. Make a sketch. Always draw pictures. Always draw pictures. Write a primary equation for the quantity that is to be maximized or minimized. Review of several useful formulas from geometry or business or wherever you're going to do. Reduce the primary equation by having a single variable to having a single variable. That's where you may use that secondary equation for that. Determine the feasible domain from the primary equation, okay? Basically, that's setting your constraints. And then determine the desired maximum minimum value using calculus. That's the procedure, okay? Now, this is not a very practical problem, but which points on the graph of y is equal to 4 minus x squared are closest to the point 0, 2? Well, obviously 0, 2 is not on it because when x is 0, y is 4. So which is that? What points on the graph are that? This one, draw you a picture, okay? 4 minus x squared is going to be parabola doing that kind of nature. There it is. And you want the points closest to that. Well, what are you trying to determine? You're trying to minimize this distance. Okay? Well, here's your distance formula. D is equal to x minus 0 squared plus x minus 2 squared. At that point, you're trying to minimize that distance. This formula is square root of x minus x2 minus x1 squared plus y2 minus y1 squared. But you know what one of the points is, so put those in and let this be your variable set. Okay. Now, that's the primary formula you're going to try to constrain. But it's got x's and y's in it. But this one also has to be met. That's your secondary equation. Y is equal to this, so instead of y, you put in 4 minus x squared. And then determine your minimum value from x's along. Then go back and plug in the y. Okay? Now this isn't going to be pretty, but it's doable. Okay? And you see they took that 4 minus x squared and put that one in instead. There's your distance formula. You take the derivative. Okay? Well, again, they're skipping lots of steps. You got to square a trinomial there, which is not trivial, but you know, it's doable. I mean, it's very easy, but it's just not trivial, okay? Because D is smallest when the expression is the smallest, you need to find the critical values for that. If you can minimize this, you minimize that, okay? So that's all you have to do. And note that the domain is the entire real number line. There's no endpoints to consider, so you take a derivative of that, you get that, find out where it's equal to 0. Okay. At x equals 0, that doesn't make a lot of sense. Let's go back here to our graph. At x equals 0, you're here. That's obviously not going to be your minimum value. That may be a local maximum, but it's not going to be a local minimum. These are the ones that are going to be local minimum. So you can throw out the x equals 0. It's obviously not going to work. So the plus 3 square root of 3 over 2 or minus square root of 3 over 2, those are going to be the ones. Okay? Sure enough, that's what you get. Oh, and you can plug in those values to get your y value. You want points, so you want ordered pairs. Always want ordered pairs. All right, that's it. Is that okay? I don't know if that was helpful or not. Okay, but that was, there's lots of good problems in that. I would say chase those down on your own. Okay. Now, 3.8. All right. I'm getting to the point where I wouldn't mind taking a break, would y'all? Okay. Okay. No one said he wouldn't mind taking a break. He shook his head. No, I'm just kidding. Okay. So as soon as this comes up, I'm going to put it, in fact, I'll put it on pause now. Weren't here before. We finished 3.6, and then we did a quick review, a quick slideshow of 3.7. You're not responsible for 3.7 because it's a, I won't test you on that, but at least one guy in the room is a industrial engineering major, and optimization problems are exactly the type of thing that they do a whole bunch of. So I wanted to at least go through that. So we're still on applications of differentiation, and here's one from the master, the guy who developed calculus in the first place. Here's one of the things he applied it to, and nobody's improved it since, okay? Finding zeros using Newton's method. So this is approximating a zero of a function using Newton's method. And frankly, nothing that I've ever seen works faster than this. The technique for approximating the real zeros of a function is called Newton's method. It uses tangent lines, of course, first derivative is tangent lines, to approximate the graph of a function near the x-intercept. And then it zooms in on it really, really efficiently and quickly. To see how Newton's method works, consider a function f that is continuous on some interval a to b, differentiable on the interval a to b, not counting the endpoints, and if f of a and f of b differ in sign, okay, f of a may be positive, f of b negative, or f of a negative, f of b positive, as long as they differ in sign, then by the intermediate value theorem, if it's a continuous function and differentiable function, then f must have at least one zero on the interval in between a and b. If f of a is here, f of b is here, got to be a zero somewhere there. F of a here, f of b here, got to be a zero somewhere in there. Okay? So that's given, there's got to be a zero. All right. Now to estimate the zero, we first choose some estimate, x1. It may not be the 0. In fact, it probably won't be the 0. But just make an estimate. Now, Newton's method is based on the assumption that the graph of f and the tangent line x1, f of x1, both cross the x-axis at about the same point. Okay? So here is the key here to Newton's method to make sure it works. If here's your function, here, f of a happens to be positive, f of b happens to be negative, so you know it's got to have a 0 somewhere in between there, because it's a smooth, continuous, differentiable function. Okay? Pick some value between a and b. It doesn't matter too much what value it is. Okay? Pick a value between a and b. Okay? Now, in this picture, it doesn't matter at all. Later, we'll see circumstances where it would matter. If this function did this, something like that, and you picked an a over here, x1 over here, where it was still going up, that tangent line is not going to be anywhere close to that 0. Okay? So that's one thing you want to avoid, is picking your x1 to be something that's not reasonably close to where you think the intersection is. In other words, the function needs to be heading in the right direction. It can't be going up here if the 0 is down here. Okay? So pick something where the function is at least heading toward that 0. Okay? Now, with that chosen, here's your tangent line. This gives you a second estimate, x2. Okay? Then you do a tangent line here, and that's going to get you an x3. Then do a tangent line here, that's going to get you almost right on C. That's what Newton's method does. It zooms in and zooms in quickly. Okay? The key here, pick your x1 so that its tangent line is going to wind up being fairly close to that critical value, the 0. It's not the same as the critical value we had before. All right, because you can easily calculate the x-intercept for the tangent line, you can use it as a second and usually better estimate of the 0 for f. The tangent line passes through the point x1, f of x1, with a slope of f prime of x1. In point-slope form, the equation of the tangent line would be y minus y1, that's f of x1, is equal to f prime of x1, that's your slope, times x minus x1. That's your good old point-slope form. So the y is equal to f prime of x times x minus x1 plus f of x1. Okay? That becomes your x2, your next best guess. Okay? And you just keep doing it. Okay? Letting y equal 0. Now, why y equals 0? You're trying to find the x-intercept of that tangent line. So set that y equals 0, and you get the new x. I'm sorry, I said before it's y. The new x is going to be x1 minus f of x over f of x prime. Okay? If you set this equal to 0, sorry about that, I said it wrong before, then you have f of x1 times x minus f of x1 times x1 plus f of x1. Okay? F prime of x, okay. They're just skipping too many steps here. Let me write this in for you because I find that a little. Set this equal to 0. Let me get my pen back. There we go. Set that equals 0 equal f prime of x1 times x minus x1 plus f of x1. Okay? Now, bring this up here and do it. F prime of x1 times x minus f prime of x1 times x1 plus f of x1. Okay? And that's equal to 0. Now, where we're going is solving for x. Okay? So probably was, well, still not bad. So let's isolate the x. So this will be f prime of x1 times x is equal to f prime of x1 times x1 plus, or minus, minus f of x1. Okay? Now, divide both sides by f prime of x1. Okay, and now you have it. See, this disappears, so we have x is equal to, your f prime of x1 disappears here, x1 minus f of x1 over f prime of x1. All right, so that's exactly what they have here. Now, that should raise another flag for you. Guess what that flag is? Your f prime at x1 had better not be 0. Right? So in other words, don't start, say if this is got a maximum here, don't start there and let that be your x1, because that derivative is not going anywhere get close to this. So the other thing is f prime of x1 can't be 0. So from the initial estimate x1, you know f of x1, or you can calculate, either f prime of x1, or you can calculate that. That gives you your second estimate. Okay? That's your x2. Okay? Then what do you do then? x3 will be x2 minus f of x2 over f prime of x2. You just keep evaluating and making another guess, and believe it or not, in very short order, you're going to be right on top of that C. Here's the example. This tangent line goes there. That gives you your x2. Then you go down to a tangent line here. That gives you x3 up here. Go up here. Do a tangent line here. It's going to be so close to that C. It's unbelievable. And then you keep going, and you're going to zoom in so incredibly rapidly most of the time. You've got it knocked. Okay? You can improve on x2 and calculate a third estimate and keep doing that. That's Newton's method. Okay? Now, here is the summary of that. Newton's method for approximated zeros of a function. And guess what? Some of you have some graphing calculators, right? Okay? And on that calculator, you have a thing there you can estimate the zeros of a function. I know you do, most of them, I mean all of them do. Okay? It uses Newton. Nothing new that's been created since Newton created calculus. This is what he used, and no one's gotten any better. Okay? So let f of c equal 0. Okay? In other words, c is a 0 for the function, where f is differentiable on an open interval containing c. Okay? On an open interval containing c. Now, then to approximate c, here are the steps. So you already know, open interval containing c, there's something to the left of c, something to the right of c. Well, c is somewhere on that open interval. Make an estimate, x1, okay, that is close to c. A graph is helpful for you, okay? And if you draw the graph, make sure you're not picking something that's going away from c, that you're picking something that's going towards c, okay? So make an estimate, x1. Then evaluate, you know what x1 is, evaluate f of x1, evaluate f prime of x1. Do the math, that gives you your x2. Plug that in here, here, and here, that gives you x3. You just keep doing it until you get within your desired accuracy. So when the x of n minus x of n plus 1 is within, say, 0.7, 0.03, whatever you want that error bar to be, you choose that. Keep going until you get there. Otherwise, you return to here. If it doesn't meet that, each successive application is called an iteration. So this is what we call an iterative process. So let's do example 1. Calculate 3 iterations of Newton's method to approximate a zero of f of x, is equal to x squared minus 2. And use x1 equal 1 as the initial guess. So you tell me what to do. Pretty straightforward. There's a couple things you got to do. You choose which one you do first.
Don't you need to put f of x on top of x, f of x?
Yes.
So don't you just do x squared minus 2 over 2x?
Okay. What he is saying, if I'm hearing you right, that f of x is this, f prime of x is equal to 2x. So he's saying, if I'm understanding right, your second estimate, x2, is going to be
X squared minus 2.
okay, not yet.
2x.
Okay. Back up one more thing. X of 1 minus that, right? Okay. So it's going to be x of 1, which is 1, minus f of 1 over f prime of 1, right? Which would be 1 minus, and what's your f of 1? Uh-huh. Negative 1 over, and what's your f prime of 1? 2. Okay, so this will be 1 plus 1/2, which is 3/2. So your first guess was 1. Your second guess is 3/2. What's your third guess?
That'd be 3 over 2.
3/2 minus, I'll write it out, f of 3/2 over f prime of 3/2, which would be 3/2 minus, what is f of 3/2?
Would be 9 over 2.
9 over 4, wouldn't it be?
9 over 4 minus 2. Is that 2.2?
It would be 1/4, 0.25. Because 9/4 is 2 and 1/4, right? And minus 2 would be 1/4. That's your numerator. What's your denominator? More like 3, isn't it? Is that what you said? Okay, I can't hear. 3, okay? So what would this be? 3/2 minus 1/12, isn't it? 1/4 divided by 3 would be 1/12, right? Yay or nay? Okay, well, it's 1/4 times 1/3, which is 1/12, right? Okay, and what would that be? Well, that would be 18/12 minus 1/12 would be 17/12. Okay, so you went from 1/3. I mean, 1 is your first guess. 3/2 is your second guess, and 17/12 is your third guess. Now, I don't know if that's 3 iterations. That seems like to me that's only 2 iterations. So let's do x sub 4. And that would be 17/12 minus f of 17/12. So I'm not looking forward to that. Over f prime of 17/12. That's not going to be a lot better. What would that be? 17/12 minus f of 17. Yuck! How sure I'm not looking forward to that. Can someone do, on your calculator will be fine, 17/12 squared minus 2. Anyone got a calculator? 17/12 squared minus 2. $289 over 144. Okay, minus 2. Right? And that's divided by 17/6. Okay? What's that? I said 6 and wrote 16. Sorry about that. Okay, sorry. Okay.
Where did you get 6 from?
Okay.
Oh, is that on the bottom?
Yeah, f prime of 17/12. This is 2x. 2 times 17/12 would be 17/6. Okay. Someone with a calculator, punch that in and see what you get.
So 289 divided by 184 is 2.0069.
And subtract 2 from it.
Okay, 0.0069.
And then multiply that by 6 over 17. Oh yeah. Let's get your real thing out of there.
And then multiply that 0.69 by what? 6 over 17?
Yeah, I was just saying invert and multiply by 6 divided by 17. And then whatever that is, subtract that from 17/12.
Okay,
4.41?
No, 1.
Wow, okay, say again, 1 point.
4, 1, 4, 2, 4, 5, 6, 8, 6.
6, 8, blah, blah, blah. Okay. Now, let's go back to the original function. Set that equals 0, right?
-2.
You get x squared equal 2, right?
-2.
No. Set this equals 0. X squared minus 2.
Oh, I thought you meant plug in 0.
No, okay, yeah. Okay. Then set it equal to 0. Add 2 to both sides. X squared is equal to 2. Take the square root of 2 and what do you get?
You add 2.
No, okay. Set this equal to 0. You're looking for the zeros for this function, right? So set that equals 0. X squared minus 2 equals 0. Add 2 to both sides. X squared is equal to 2. Take the square root of both sides. Square root of 2 is?
1.412135.
See how close you got? Really close in just 3 times. 3 tries, you were really, really close. Okay? So, Newton's method generally works quite nicely. Okay? Now, they do a table and carry it on out, and they rounded that last one to 1.414216. They didn't carry as many digits as you did. You can plug it again and again and again. Soon you're going to be right on top of square root of 2. Okay? That's how we did it. Let's see how they did it. I think it's going to be pretty close. Okay? Because f of x is that, f prime of x is that, and the iterative formula is x to the n minus n plus 1 is x to the n minus f of x to the n divided by f prime of x to the n. So x to the n minus x to the n squared minus 2 over 2x to the n, exactly like you were saying. And then you just plug in, for x of 1, you plug in a 1. Okay? And then they show you each one of those steps, and basically just like we did, we got 1.5 or 3/2. Then they did plug that in, and you get L sub n was 0.25, 1/4. L prime was 3. Plug that in, you get 0.08. Do your subtraction there, and man, you're getting relatively close, 1.416 rather than 1.414. Plug that one in, your f of this, f prime of that, the ratio of that, subtract that from this, and you get that. And that's what we wound up with, awfully close to the square root of 2. Very, very close to the square root of 2. And you're getting there. Of course, in this case, you know that the two zeros are plus square root of 2 and minus square root of 2. We did that one. 1.414214. We had 1.414216. What's that? 6 decimal places. We got within 2 on the 6th decimal place. That's pretty good for 3 iterations. Okay? And that's what they say here. You have attained an approximation that's within 0.00002 of the actual root. Mighty good. Okay. And here's what we were going by. The first iteration was x equal 1. The first derivative was up here, and you got 1.5. Awfully close to that. Second iteration was that one. Do a tangent line down there, and you're incredibly close to that root. And you just keep going, and you get just as close as you. Actually, what you do, you run out of precision on your calculator before you do. You get right on top of it, basically.
How do you run out of precision?
What's that?
I said, how do you run out of
Precision on the calculator. Well, you notice you're taking a subtraction there, right? It's x of n minus f of x of n over f prime of x of n. When that ratio there gets to such a small number, your calculator is only good to probably 10 to the minus 12 or something like that. And when your difference there is within that, when you subtract, you're within the precision of the calculator, and then you start getting meaningless numbers. Okay? So that's what's going on. That's numerical analysis will give you that. Okay. Now, when, as in example 1, the approximations approach the limit, the sequence of those approximations are said to converge. Moreover, when the limit is c, it can be shown that c must be a 0 of f. Okay? That's what we started off. Newton's method does not always yield a convergent sequence. Okay? And here is why. One way it can fail is shown here. If this is the 0 you're looking for, this is what I was telling you before, and here's your function, and this function happens to have a place where the first root is 0, Newton's method fails miserably. If you're anywhere, I don't want to say that. If you happen to start at this place where the first root is 0, you can't do it because you're dividing by that first root. So that's certainly going to fail. Okay? Absolutely. Every time. Okay? Now that's if you just happen to pick really poorly. Okay? Because Newton's method involves a division by f prime, it is clear that the method will fail when the derivative is 0. Okay? When you encounter that problem, you usually overcome it by choosing a different value for x1. You just happen to choose the one place where it was 0, choose a different one. Another way it can fail is shown in this example. Now they're skipping example 2, so let's go back and do example 2. Okay? Use Newton's method to approximate the zeros for f of x is equal to 2x cubed plus x squared minus x plus 1. Okay? Continue the iterations until two successive approximations differ by less than 0.0001. So your I don't know what to call it. I want to call it P, but that's not really the best thing to call it. Let's call it E, is less than 0.00001. In other words, your error, your difference between those two. Did I write it right? No, only 3 zeros. Okay. Okay. Now,
What's the x? What's the x?
what's that?
What's the x?
What's your x1? You have to choose. Okay? Let's talk about that for a minute. Okay? Now, what we want is the zeros of that function. Now, you can plot it into your graphing calculator and see what one of the zeros might be. I'm going to suggest this to you. What happens if you put x equals 0 in? Then this thing, alpha 0 is going to be 1. Okay? Well, that's not far from being a 0, so why don't we just use I would say either use 0 or 1, just as a starting point. Okay? This could have up to 3 zeros. So pick something, and you're probably going to get close to one of those zeros. Okay? Let's just pick another one that's pretty easy. X equals 1. That would be 2 plus 1 is 3. Minus what? So that would be 3. So 1 is not really close. I'd say let's go with 0. Why not? Okay, let's try 0. So let's let our x1 equal 0. Now what else have you got to calculate here? Help me. Second?
You do 0 plus. You do 0 minus fx.
Okay. You're going to need to do alpha 0 for sure. Okay. What else are you going to need?
Derivative.
Let's do the derivative. F prime of x is equal to 6x squared plus 2x minus 1. All right. So if you do your x1 to be 0, just why not? Okay. Then your x2 is going to be x1 minus f of x1 over f prime of x1. Okay. Which is going to be 0 minus, and you plug the 0 into the f, and you get 1, right? And plug a 0 into your f prime, and you get a minus 1. Perfect. Okay? So that's going to be 0. That's just going to be 1. Okay? So there's your x2. I'm not liking this too much, but let's see what happens. X3 is going to be X2, which is 1, minus f of 1 over f prime of 1, which is 1 minus, and what's f of 1? We did that earlier. It'd be 2 plus 1 is 3. So I think that's going to be a 3 over f prime of 1 would be 6 plus 2 is 8 minus 1 is 7. Okay? So someone, okay, I don't know. Let's just call it 4/7. Okay? X4 is going to be 4/7 minus f of 4/7 over f prime of 4/7. Now at this point, let's start using a calculator, okay?
Why is it positive 4%?
Okay, I don't know. Is it supposed to be negative?
Well, you have 1 minus 3 over 7.
Okay. Where are you? This line right here? Okay. So f of 1 will be 2 plus 1 is 3, and then plus 1 minus 1, that's going to be 0. So that would be a 3 in the numerator.
No, I see why you get the 3 over 7. So is it 4 over 7 because it's 1 minus that?
It's 1, yeah, 1 minus 3 over 7. You got the 7 here too. So 1 minus 3/7 is 4/7. So this is 7/7 minus 3/7 is 4/7. Yeah, okay. It's higher level math. All right. Now at this point, please use your calculators. I'm not going to figure those out in my head. 4/7 minus 2 times 4/7 cubed plus 4/7 squared minus 4/7 plus 1, put those all in parentheses, divided by another set of parentheses, 6 times 4/7 squared plus 2 times 4/7, or 8/7 minus 1, that's in parentheses, and hit your equal sign and see what you get. Be sure you do this in parentheses and that in parentheses. Unfortunately, it takes a while, doesn't it? Now, if you have a programmable calculator, I don't know if you do or not, but you could just put the function in there and the derivative in there, plug a value, and it can spit those things out for you. I don't have one, so I can't say how hard or easy that is, but that's sort of the way to go, ultimately. Anyone come up with anything yet? They use decimal numbers, which probably work out.
Is it 0.03467?
Okay. That's the thing I don't know for sure, but it sure sounds like that's a reasonable answer. They happen to choose a different one to go for. Like I said, this has 3 zeros. I chose the one near 0, they chose the one near negative 1.2. So we're going to wind up with different values. But you see, it will zoom in there. What was that number you just said. Say it again.
0.034674063.
Okay. 0.03467.
Yes, sir.
Blah blah blah. Whatever else.
406.
4060. Okay. Tell me what 4/7 was. 4 divided by 7. Much bigger number.
0.571.
Okay. So you see, you haven't gotten really close yet. But I bet you the next time is going to be something much closer to that. And, you know, you probably zoom in there pretty quick. But since they went to a different one, let's not take any more class time doing it. Okay? Now, I've got that it's,
7 minutes.
10 minutes you got? Okay. Let's see if we can get example 3 to happen. Here's example 3. Here's an example when Newton's method fails. Here's f of x equal x to the 1/3. Okay? It is not differentiable at x equals 0. Is that true or not? What is f prime of x? Anybody? Yes. Okay. It's a power thing, right? 1/3 times x to the negative 2/3. Don't be shaking your head at me. Okay. Now, what's wrong with x equals 0? That's the same as, by the way, 1/3x to the 2/3, right? And when x equals 0, huh?
Or that could be 1/cube root of 3x squared.
Okay, I couldn't get
1/cube root of 3x squared.
Yeah, 1/cube root of x squared. But when x is equal to 0, that's undefined, absolutely. So therefore, it's not differentiable at x equals 0. And it says, shows that Newton's method fails to converge when you choose your first value as 0.1. Because you're choosing a value awfully close to an undefined value. Okay? And you can, it says show that. I have a feeling that's going to take a little bit of time to show. So since we don't have, I don't think, time enough to do it, let me just let them show you, okay? You okay with that? I normally don't do this. I usually want you to work them out, but let's just see what happens. Because f prime is just what we just did, 1/3 x to the negative 2/3. So x of n plus 1 will be x of n minus f of x n over f prime of x n. So when it's equal to 0.1, okay, yeah, they just put those in, okay, so at 0.1, oh, here we got it. It was a lot easier than I thought it was going to be. So let's go back and do it. Okay. Yuck, I already erased it. F prime of x is equal to 1/3x to the 2/3. Okay? Second? Yeah, but I put it downstairs. Right, okay. So, here's what we have. X sub n plus 1 is going to be x sub n minus x to the 1/3, I'll put an n there if you want it to, over 1/3x to the 2/3, okay? Which would be x sub n, this will be an n here, okay? Minus Now, I'm going to invert and multiply. Okay? In other words, this is going to be x sub n to the 1/3 times 3x sub n to the 2/3. Okay? Well, this will be x sub n minus, okay, 3x sub n to the first power. Okay? Now, notice what happens there. That is your recursive formula, no matter what n you put in there. So let's do x2 is equal to x1, which is 0.1, minus 3 times 0.1. That would be 0.1 minus 0.3, which is negative 0.2. Then you do x sub 3, that's going to be negative 0.2 minus 3 times negative 0.2, which would be negative 0.2 plus 0.6, which is going to be 0.4. Okay? Now, I don't know if you notice what's happening here. The first iteration is first estimate is 0.1, then negative 0.2, then positive 0.4, then negative 0.6, and then positive 0.8. They're getting further and further away. Okay? And why is that the case? Okay? Let me clear this out of the way, and hopefully they'll show you here before we run out of time. Okay? That's negative 2x. So basically what I was just saying, every time you're getting further and further away from your initial point. There's no reason to go through that previous formula, that x to n plus 1 is going to be minus 2 times x to the n. Okay? So when this is 0.1, negative 2 times that is negative 0.2. Negative 2 times that, 0.2 times, negative 2 times that would be positive 0.4. Negative 2 times that is negative 0.8. The next one's going to be positive 1.6. The next one will be negative 3.2. It just keeps getting further and further off, okay? Not going anywhere. It's diverging, okay? And here's why. Look at this. Remember we said that the first derivative was not defined here? Okay? You picked a point awfully close to there. That tangent line is going to take you back here. On the other side of 0. This tangent line is going to take you over here. Back on this side. This one's going to take you further here. This is going to take you further there. You're getting further and further away. Okay? Here is the key, folks. Okay? If you're wanting to estimate a 0, you're going to have a value. Well, this one will basically never work. Why? You've got it very close to the vertical tangent line there. So that's not going to get you anywhere close. It's going to get you further away. Okay? And you just keep going. So the key here is, well, this one you're just never, there's no place you can start and not get further and further away. So don't do it. Don't use it for those cases. So what you want to do is have it so your first derivative is pointing closer to 0 than your initial estimate. And this one's pointing further away. But once you start going further away, you're never going to get closer, most of the time. Okay? Now, I think we're out of time, aren't we?
Yes, sir.
Okay. So we'll start at the top of page 232. Okay? Now, let me give you a few. Oh, goodness, we almost finished that. Do either 3 or 5. They're both at calcchat.com. 3 is at CalcView. Do any of the odds 7 through 15. They're both at all at CalcChat. 9's at CalcView. And then we'll pick up the rest of those next time. Okay. We still got differentials to do. Man, I keep forgetting this is such a long chapter. We'll finish 3.8 next time. We'll start, and 3.9 is very, very short too, and then I'll give you your test next time.
See, this is what I was talking about earlier.
Okay. Have a good
Yeah.
one.
This is the
All right.
first F prime.
Right.
So you know it increases from a negative infinity,
Right.
and then at 0 you see it goes down. I
Right.
was just wondering if you ever taught that.
Yeah, I've used that before too, but when I can see it without doing that, I just go on and do it. But yeah, that is a good, rigorous procedure to do. Thank you so much. Okay, to go. Yeah, that is a good way to go. Yeah. Did you have it in high school or in college?
I learned it in college.
Yeah. Did you? Yeah. And I take it you found it useful.
It works with like for the double prime, yeah.
Right.
F double prime.
Right.
When you do the concaves, like I like to
Right.
do like on positives, I'll just draw like a
Right. Exactly.
half parabola and then
Yeah. It's a great technique to do. It is.
I was
All right.
kind of how to do it, so I was wondering if you good.
Yeah, I probably should take the time to go through all that. But Chris, what's that?
Test 1, I lost like the paper.
Say that one more time.
I lost the paper of test 1 and I wanted to turn it in, but I lost it. I was wondering if I could get a second sheet.
You mean you want test 1 over again? I don't know if I have a spare copy. Have a good weekend. See you Monday. Okay, let's see if I have an extra one. I should. Let me see if I do. I don't know why I don't, but it doesn't look like I do. So let me, there it is. I do have one. It was stuck on the back of that page. There we go.
All right, thank you. I'll
All
turn
right.
it in next week.
Okay.